All right, so I lumped this together with like our rate of change problems because it tells us that something is increasing or decreasing, right? Yeah. The oil slick is increasing at 2,000 cubic centimeters per minute. So what is that? That's a derivative, right? That's a derivative of the volume, dV dt. And it's a constant, so it's not really doing anything crazy. It takes the form of a right circular cylinder. It's just a big flat puddle, basically. But they're saying it's a cylinder because it has like a little bit of thickness off the water. Okay? And this question here is a related rates question. Okay? They're telling you how fast something's changing, the volume, and they're asking you what's the rate of change of the height of the oil slick with respect to time. Okay? They're also giving me the fact that the radius is increasing by 2.5. So remember we said with these related rate kind of situations, which is kind of weird for them to throw it out here in a free response question, is to list out what we know. We know dV dt is 2,000 cubic centimeters every minute. And we also know the rate of change of the radius, dr dt, is 2.5 centimeters per minute. That's in centimeters because it's a radius, it's just a length. The volume is in centimeters cubed because it's three-dimensional. Okay? At that instant, what do we know here? The instant when the radius is 100. So we also know at the point we care about, r is 100, but it's changing. But I'm going to write that out anyway. Okay? And we want to know how fast is the height changing. So that is our desire, is to know what's dH dt. So we said with these kinds of questions, you want to link the rates you know to the rate you want to know. Cool? And since we know the rate of change of volume and the rate of change of radius, and we want the rate of change of height, if I can get an equation that has volume and radius and height in it, then I'm good to go. And it turns out that since it's a cylinder, the volume of the cylinder is just pi r squared h. And remember, we're not really interested in the volume necessarily, we're interested in the rate of change of volume, so what we're going to do with this equation is derive it with respect to time. Okay? So when you derive v, you're going to get dv dt, that's nice. When you derive the other side, we got to use the product rule, because we got r squared times h. The pi just kind of hangs out front. So when we derive r squared, we get 2 pi r dr dt times h. Okay, that's driving r, leave h alone, and then add pi r squared, leave r alone, derive h. And the whole point of that is getting us an equation with a variable we want to know. We want to know what dH dt is. So this is what we're looking for right here, which means we need to know what r is, what h is. So we need this, we need this, we need dr dt, we need r, and we need dv dt. We've got to find all those other variables. And they gave them all to us, right? We know dv dt is 2,000. We know r, they told us, is 100 centimeters at this point in time. I know that like that 100 sometimes kids want to plug in to the volume equation. And you don't want to plug in anything that's changing until after you derive. Okay, so that's why I didn't plug that 100 in there when we did this. But now I'm plugging it because we're already done deriving it. And dr dt is 2.5. You can worry about the units here, but they're all just going to kind of work themselves out. And then we don't know what h is yet, do we? Did it say in the problem anywhere? Oh, it does say h is 0.5? Oh, it does. I skipped right over it. Boom. H is 0.5. Cool. If we didn't know that, we'd have to go back and find it with the information given in there, but they told it to us. So h is just a half. Cool. Plus, we know pi. R is, I wrote 2.5. I'd rather use fractions here, but, I mean, we're going to use the calculator anyway, so it doesn't really matter, but it's a 5 halves there. And then pi times r is 5 halves, but we're squaring that. And then we have dH dt. So we get all that going on. It's okay? And now we just got to simplify it out. Again, you've got a calculator for this, but we can do this pretty much without a calculator. That's 2,000 equals. Over here you have, so look what's going to happen here. This 2 is going to cancel with this 2. This 2 is going to cancel this out to a 50. So you have a pi times 50 times 5. So it's 250 pi. Yeah. R is what?
100. So R squared you put in 5 times.
For r squared, oh, I put in dr dt. Thank you. You're absolutely correct. That is 100 in here. Excellent. Did you all see that? You watching me do this and you don't let me know? I'm making a video for the masses online. Okay. So 250 pi on that side. That's correct, right? Yes. Okay. And then we're going to have plus pi times 100 squared is just 10,000 pi dHdt. And solve that, we're going to minus 250 pi. So it's 2,000 minus 250 pi, and we're going to divide by 10,000 pi. And that is what dHdt is. You can drop it in the calculator. You can simplify out a couple zeros here if you really want to. Remember, free response, you don't really have to simplify out at all. You can just leave your answer like this. But you got to put units on here. So the units on the rate of change of H are centimeters per minute. No, it's, a lot of times you don't see related rates at all. I mean, so you get these like rates to change things that you got to work with, but not necessarily a related rates question like this. There have been a few, but they're not every year. They don't do that. All right. So we're feeling okay with that? All right. Can we do B? So right now we have a rate into the oil slick. It's 2,000 cubic centimeters a minute, right? That's how it's growing. And then all of a sudden in B, they say, hey, a recovery device shows up, and now it's removing oil. So that's a rate out now. So now I got a rate in, and we have a rate out. Okay? So the derivative of the amount of oil is the subtraction of those two things. Okay? So T is in minutes since the device began, blah, blah, blah. Oil is still leaking out at 2,000 cubic centimeters per minute. Find a time T when the oil slick reaches its maximum volume. Notice here, it doesn't give us a point. Do you see that in this question? Like, they don't tell us how much oil there is ever. So they can't ask me in part B how much oil is there at a certain time. They can't do that because I don't know how much there was to begin with, right? But they can ask me, like, how fast is it changing, because I know the derivative. So when they say, find the time when there is a maximum, they're not asking you to find the maximum. They're asking you to find where the derivative changes from positive to negative. That's where a maximum is going to happen, and that's the best we can do. Okay? So I told you with a question like that, what you should do is make up a function. So when you got a rate in and rate out, let's let A of t equal the amount of oil in the slick at time t. Okay? And that automatically means then A prime of t is what? How fast is it growing? What's the rate in here, kids? 2,000, thank you, 2,000. And the rate out is 400 root, just root t? Is that all it is? Okay, cool. Can we handle that? That's my rate of change. So we're going to have a maximum when this derivative changes from positive to negative. Now we can't find out how much oil is there, but we can tell when the max is going to be. Cool? So we know to find maxes and mins, you set the derivative of what we're trying to maximize equal to 0, and you solve this. So that's going to give me this. You get this going on. We're going to divide by 400, so that gives me 5 equals root t. And then we're going to square it and get 25 minutes equals t. Now I promise you, since this is the only critical number we've got, that's going to be the maximum. Okay? But you still want to explain why it's the maximum. All right? Because they ask you to explain most of the time here. I didn't see what they say in this one here. But yeah, they say justify your answer. Okay? So we're going to justify this by showing the derivative changes from positive to negative there. Okay? So we're going to make a little number line here like we've been doing, but now your number line is never justification. We still have to write a sentence, but this is just for us to make sure that we see what's going on. So we know time starts at 0. We know our only critical number is 25. If I take a number less than 25, 1, and plug it into my derivative, we get a positive value. Cool? So the derivative is positive A prime of t, which is what I'm going to call it. A prime of t is positive there. If you plug in a number bigger than 25, something we can take the square root of, like 36, okay, you're going to get that this is negative. So what's that mean the oil is doing starting out at 0? The amount of oil is increasing all the way until 25 minutes, and then starts to decrease. So without knowing how much oil there actually is, we still know the maximum happens at 25 minutes. Okay? And then we just got to write a sentence explaining what we did so we get full credit for this question. So it says, find the time when it reaches the max, justify your answer. Cool? The amount of oil reaches its max at t equals 25 minutes because, and look, since we named what A of t and what A prime of t are, we can talk about them. If you don't make up A of t at this point, then you got to talk about like the rate of change of oil or something like that. Okay, like you got to write down words. But if you just call it something, you can just use this letter. So because A prime of t is positive, so you don't just want to say that it changes sign at 25 like this. You want to say that it's positive the entire time, which means there's no other possibility for there to be a maximum. So it's positive on the interval 0 minutes less than t to 25 minutes, and negative on the interval t is greater than 25 minutes. That goes to infinity, so you're going to say that. Whew. Make sense? Again, you see like these rules that we've seen before kind of mishmashed together with a couple different concepts. But finding maximums always happens when the derivative of that thing changes from positive to negative or at an endpoint. And the only endpoint we have here is 0, and that's a minimum amount. Okay? And then in C, I think they actually give us a point of time here. So by the time the recovery device comes in, 60,000 cubic centimeters are already there. Write but do not evaluate an expression involving an integral that gives the volume of the oil found in part B. Hopefully we're like good at this already here. So what are we going to start with? The amount at time 25 is what they're asking us. We have to start with what value? 60,000. Cool. And they're nice. They say don't even evaluate it. Just write it out. Okay? So the amount at 25, which we can use A because we named it already and called it what it was. You start with 60,000. I'll get that door in a second, okay? Times the plus the integral from when we know it's 60,000 to when we want to know what it is, 25 minutes. And you could put in 2,000 minus 400 root t, or because I named A prime of t that already, I can just write A prime of t here, dt. Okay? And that's just our big rule for derivative. You know a derivative, you know a point. That's how you write out that function. Okay? Sometimes they'll say this. This is a different question, but they'll say write an equation that can be solved for when the amount of oil will be 0. Okay? Like because the recovery device is there taking it away, right? So if the question was that, we wouldn't integrate to 25. We'd integrate to just like t, like some time we don't know. And we'd set the whole amount equal to 0, which is what they're asking us. Like, when will A of t equal 0? Well, we know what A of t is. Just set it equal to 0, and that's basically what they're asking you to do. Okay? So you see that sometimes.
Right.
Cool. What's up, man?
When we put it, like, for the integral, would we put 25 on the bottom and then we just put, like, a random variable on top? Like,
No, because you don't know what it is at 25. You know what it is at 0.
so you have to put...
You always, this x value here has to match up with that y value, always. Like if...
No, I understand.
Well, doesn't the recovery device come in
Because
at
we don't know
25?
Yeah, but once we know what it is at 25, now I can use that value plus the integral from 25 to t as well. Yeah, so if you do multiple points, then you can write the integral multiple ways. But x and y have to match up as 1 point. Okay?